Hello everyone, it's August 11th. Alright, back to morning. Well, it's actually no longer morning anymore. It's almost afternoon. Let's do this. What do we have today? Array of doubled pairs. Given an array of integers of even length, return true if and only if it is possible to reorder it such that array, this is odd position equals 2 times even position for every I, 0 to the half. So, which means array 0, array 1 equals 2 times array 0, right? Array 3 equals 2 times array 2. So, yeah, every odd position value equals 2 times the even position value to the left. Okay. If and only if it is possible to reorder it. So we can reorder it any time, any way, just to see if it's possible. I mean, in this case, well, 3 and 6 we can do, but 1 and 3, there's no double. Which means the odd position must be an even number, right? The odd position must be an even number, and this is not possible because 6, there's no 3. This is true because we can say -2, -4, and 2, 4. Three times 10 to the 4th is the length. The length must be even. Okay. We just need to find if it's possible. All right. All right. Let's look at the last. Let's look at the last one. I mean, the previous one. I mean, what we can do is we can just take out all the even numbers, all right? We'll take out all the even numbers and divide them by 2 and see whether we have any, when I divide by 2, we'll have more even numbers, I think. That's what we have. So the last one, if we take out, so the odd number must be, take out the odd number first. Oh my god, this one only have one odd number. So odd number is 1, right? So if to make it work, the odd number multiplied by 2, the odd number must be in the even position, and then multiplied by 2, so equals 2. So the even number, we have 2, 2 have 1 count, 4 have 2 count, 8 has 1 count, 16 has 1 count, right? So what we require is a 2. And then we see, oh, we have a 2, so 2 gets checked out. So we don't have any more odd numbers. So now the business is all about the even numbers. So which means among the even numbers, some even number need to be placed in the even position. So what do we say? Well, what we have is 4, 8, and 16, all right? We say, I mean, the largest one, 16, we can go larger to small. Like the largest one is 16. The 16 cannot be placed in the even position. 16 must be in the odd position. So we say 16 will have to divide by 2, so 8. So we need 8 and 16 pair. And then 8 and 16 pair, we're done. And now what remaining is 4 and then 4, which is 4, right? So 4 is currently the largest, so we need to say 4, we need to divide it by 2, which is 2. We require 2 4 pair, but we don't have 2 anymore, so that's why this is now good. Okay, so what's the strategy? Well, the strategy is first get all the odd number out. So we get the odd number out, and we count all the even numbers. Now for each odd number, in order to make it work, we multiply by 2, and then so we clear out all the odd numbers and see if there is an even number that can pair with the odd number. If we cannot pair, that means it's going to be a false, right? We already eliminate the possibility. If we can pair, then we just remove from the counter all the even numbers count, right? And what we are left with is all the even numbers, and then we need to make the even numbers work. Now, how do we do that? Well, what we can do is, given the even numbers, right? Given the even numbers, we go from large to small, right? Large to small. So we go from the largest even number, and we take it out, we divide it by 2, and then what we can do is put all of these into a priority queue. So we always pop out the largest. So largest pop out, and the largest can only be divided by 2. So we divide by 2. We find if the quotient exists in the counter. If it exists, so both will decrement, right? Both decrement. And we keep going, right? And in that case, we actually just directly put, we cannot directly put, yeah, we do need a counter because we want O1 to check, and we want O1 to check. But if you sort it, we can sort. We sort the keys, right? And then we go, and then we just one by one, right? So this one, the largest, done, and then we have still more. We check the largest again. Then if it's no good, then no good. The largest done, then we move the pointer one position to the next one, which is the next largest, and then we check if it's, yeah, that shall be, yeah, I think this shall be the good strategy. Let's give this one a shot. So basically what we're saying is do it in 2 rounds, right? So we don't need deck, but I do think, no, we do need a counter though. I think we need a counter. Anyway, so we don't need all of these. All right. What we want to do is get all the even numbers and get all the odd numbers. So for A in array, right? So odds equals this, and even count equals a counter, right? So if A is an odd number, odds dot append A, else even counter A equal 1, right? So we get the counter for the even values, and then we're going to say for O in odds, right? For O in odds, if O times 2 not in even count, turn false. Else, if it is in, then even count O times 2 minus equal 1. If not even count O times 2, then even count or remove O times 2. Right? We just, if we count to 0, we just remove it. Is that how it's working? I actually don't know. Not 100% sure, but we're gonna check. I forgot. A equals counter. Just say 1, 2, 2, right? And then say A dot remove 1. Nope. Has del A1? Oh yeah, it's del. It's not remove. It's del got it wrong. Alright, so we decrement and remove it if we need to remove it. So now we go through all the odds, and if it's not working, we already handle it. If it is working, we handle all the even counts. Now we add even counts. What we need to do is to create a sorted list. So for big even, right, in even counts.keys, are going to be sorted even counts.keys, reverse equals true, right? So we want a sorted. So this one come out, and what happens to this one? So big even, and we say if big even, we can actually combine this, right? We can just say even count, yeah, so even count minus 1. We say if even count, this is smaller or equal to 0. Oh, hold on, that's not. So minus equals 1, right? And then we have two scenarios. We have no, I don't like it. I think this is better. So this doesn't exist, then we just return. If it exists, we decrement, and then we remove it. Yeah. So the same thing, if big even divided by 2, not an even count, return false, right? And then else even count, big even divided by 2. I just call it false. Potential equals O times 2, right? And then all the O times 2 can be changed to pot. Here's the same thing. Pot equals big even divided by 2. Actually, we need, hold on. So sorted evens equals this, right? And then I equals 0, while I smaller than sorted evens, blend sorted evens. Potential equals sorted evens I divided by 2, right? And if we say the potential is not an even count, then we immediately false. Otherwise, potential will be minus equal to 1, right? And then even count sorted evens I also minus equal to 1. Alright, so both minus equal to 1, and we check every single one. If not even count pot, then del even count pot. This, if not even count sorted evens I, actually, we don't have to delete this because we won't be encountering it again. So we just need to handle the pot, the potential, right? We just need to handle the potential. Or do we not delete it? I mean, we don't have to delete it. We check every single one, right? Yeah, we check every single one. So yeah, we just say potential is equal to, so for I in this, right? And we say if if even count sorted evens I, right? If this is larger than 0, then we do all this. If it's smaller than 0, we just skip it. If it's larger than 0, So potential is this divided by 2. So if it's not an even count, if even count part is equal to 0, return false, right? If even count is equal to 0, then we return false. It's the same thing. Let's just use even count part equal to 0, return false. Otherwise, even count part minus equal to 1, and that's it. Okay, we don't remove it. Minus equal to 1, and the even count sorted evens. So we use sorted evens many times. So we say big even equals sorted evens I. So all the sorted evens will be written as big even, right? And then it's going to be big even also minus equal to 1. Yep. So yeah, so we do that and then go back up. And then what do we do I? And we say if not even count big even, which is, I can just say if not. I can just say if not. Say if not is equal to 0, which means we exhausted it I plus equal to 1, right? Otherwise, alright, so if this argument is 0, and then actually do it here, right? If it's 0, big even equals this, and then we check. If it's larger than 0, we do this, and after this, we do this. Otherwise, which means it's already equal to 0, then we do I plus equal to 1. We go to the next sorted evens. And we go through this, and eventually we can return true. Okay, so I have a fair amount of test case 3130. Right, this one shall be false. Next one, 2120. This one shall be false as well. Next one, 4 minus 2, 2 minus 4. This one is true. Next one, 1, 2, 4, 16, 8, 4. This one is false. Okay. Array should be can array run it. Oh, 0, 1, 2. Test 2 fail. I think it's the true fail. Okay, let's take a look. I mean, we don't have, I just says print sorted evens, right, and print even count. Sorted evens is this. Oh, snap. Snap, snap, snap. Oh, we have negative values. Well. Negative values. Huh. So we have to prepare two different batches, right? Because the negative will only handle with negative, and the positive will only handle with positive, because of times 2. So the original can be divided into 2 parts, negative part and positive part. And actually, we can turn all the negatives into positives, because it's the same, because the negatives can only handle with negatives, right? So if we turn all the negatives into positive, that's actually not right. We shall take all the negative out and all the positive out. So we have 2 separate. Okay, but the odds part still works. This part still works. But this part doesn't really care, right? This part doesn't care. What cares is this part, which means we have to well, I mean, we can do another count. Huh. Okay, so you have to say, positive evens and negative evens. Right? Positive evens will be key in even count of keys if key is larger than 0. Larger equal to 0, that's fine. So for key in this, if so the key, and I want to sort it, and I want to reverse equals true. So that is positive, and negative evens equals the exact same thing, but this if k is smaller than 0, and we do not reverse. We want to small first. And we can actually do a check. Okay, if len positive evens is divided by 2, or len negative evens. If any one of these is a odd number, which is it possible? Oh, given us all even numbers, and then we take even number out. It is possible. It is possible. If anyone the length is odd, then we return false because we cannot handle it. And then we're going to do this, which can actually be, say, def check evens, right? Check evens, even array, sorted even, sorted evens, all right? And then what we're going to do is just do this. It's going to be a list of integers, and we're going to return a Boolean value. So I is this, I is smaller than this, big even, blah 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 blah, return false, return true. And then we just call check evens, return, check evens, evens. We can actually do it inside. We say if len sorted evens is this, we return false. Alright, so we don't have to check here. And then positive evens and check negative evens. So with this pass, let's try the ones without negative. They all pass. Alright, let's give this a shot. It's also including this. Probably don't have to. I think I don't have to include counter. They probably just import everything. Alright, try to run it here. False. Alright, let's see. Pending, judging. Alright, wrong answer. 0, 0, edge case. Shoot. 0, 0, edge case. How 0, 0, edge case is not handled? 0, 0, we shall give in the check even. That's considered positive evens, right? All right, don't panic. No panic. We just have a bit of issues here. So let me just print positive evens. Yeah, there's this, and then count, even count. Yeah, so it comes in. Oh, shoot. I cannot do it this way. Yes, because have repeats. Mamma mia. So that actually means we need a sum. And that's too much trouble. That's just don't do it. Yeah, that's too much trouble. That's way too much trouble. So what we do is just don't do this. All right, I'm gonna try it again. I'm actually worried about other edge cases. Let's try a few other edge cases, such as a single value. A single value. Well, no, that's a test case is wrong. It must be even number. So we can check an empty case. That is an edge case. That returns true as expected. That's like a 1, 1. Right, this one shall return false. Yep. All right, let's try it again. Pending, judging, accepted. Okay, yeah, this one is not too bad, but I got a little bit mishap here because I thought the positive evens and negative evens they include every single one, but no, we're taking all the keys. Right, we're taking all the keys, so that's not how it is supposed to be. Anyway, so first we get all the odd numbers out and create a counter for all the even numbers. Since the odd numbers can only be multiplied, we can check 2 times odd, then we check whether 2 times odd is in the even numbers. If it is, we decrement the counter, the even number counter, the even number counter. Otherwise, we can return false. We can return false immediately. After checking the odd numbers, we now check the even numbers. Note that we can have both positive and negative negative even numbers. The good thing is that the positive even number can only be paired with other positive even numbers. Same for the negative. Thus, we can write one function to check both the positives and the negatives. To check, we go from the largest even numbers, down to smallest, because the largest even number can only be divided by 2. For negatives, we go with the largest negative number. For each big even number, we check whether big even divided by 2 is in even counter. Decrement counter for all even numbers. We should mention this can be even count, right? Multiplied, check is in even count. If it is, we decrement even count. All right. We check whether if it is if whether has more than 0 count in even count. If it does, If it does not, we return false. If it does, decrement the count, decrement even count. So both big even and big even divided by 2, and continue. Continue until we exhaust all even numbers. So the runtime is when we have a sort. So runtime is O(n) log n. We have the sorting part, which maybe it's not ideal. Let's check. We hit a 676 milliseconds, or a 63% ranking, which is mediocre, as our name perfectly signifies. All right, this one probably has solution. Yeah, it does. I mean, it's not really like a difficult question. It's just it's linear, like straightforward analysis. 954. But I saw greedy. See, that is the thing. Greedy. Test case is so weak. No, it's not wrong. All right. Greedy. We sorted by absolute value. Nice. And we counter. If x is currently the array element with the least absolute value, it must pair with 2 times x. And the other x divided by 2 to pair with it. That is, I think it's the same, but okay, so we check x times 2, and then we minus. Oh man. Yeah, basically what this is saying is we can combine the odd check and the even check together. Holy moly, yeah, this is true. But hold on, what if it's, yeah, we decrement, but then we move on to the next one. Right, we move on to the next one. What if we have a lot of small values? Like, have like 2244. I think about 2244. And this will give us sorted A, right, will give us 2 and 4. So 2, and this both exist, so decrement, 2 and 4, and then we go to 4. Hold on. I do not understand. Let's say 2244. The output is true. How? That'd be 2. So for x in sorted A, right? Sorted A is going to be 2 and 4. Oh, hold on, sorted A. Ah, yep. Okay, yep, this is correct. This is correct. I mean, it's the same idea. Yeah, we can sort the entire thing. Let's check even now. We're making this a lot more complicated than it's supposed to be. All right, let's do this. Yeah, we can combine everything. So solution 1 is unnecessarily complicated. We can easily combine all 3 situations, odd, positive even, and negative even, into one overall, into one algorithm. All right, reference is the solution. Right? Nope. I want the. Oh, I cannot get a URL. There. Yep. Into one algorithm. So, into one algorithm, we're gonna have count equals counter array, right? And for A in sorted array, key equals ABS. Nice. This is a good trick. Good trick. Key equals ABS. All right. So now, for A in sorted, we say if count A equals 0, if not count A, if count A, right, and A is a small value, so we can only go double, right? So we say if count A, and if not count 2 times A, return false, right? Otherwise, we say count A minus equal 1, count 2 times A minus equal 1. We have very clear logic, and then return true. Actually, we can also say if count A and not count this, right? So either not count A or, yeah, I think this one will work as well. Oh, hold on, it won't work because I'm, no, I have to do it this way. Let's return true. Okay, so solution 2, yep, this is a correct way to do this. Submit. It's actually slower, but doesn't matter. That is the right way to do it. Greedy, oh, and log in because I'll just sort. Anyway, that's it. Yeah, combine all 3 situations. Yeah, it is true. Like, we can combine all. I think the reason that we didn't figure it out because we just, yeah, at the very beginning, I was like, okay, the odd numbers. I just get rid of all the odd numbers. When I start thinking that way, kind of losing the opportunity of combining everything together. But the odd numbers and even numbers are the same, right? And also because in here, the odd numbers are trying to multiply by 2, and the even number are trying to divide by 2. I betcha if I started thinking, instead of going for the largest, the small, I start thinking from the small to largest, and I say, okay, multiply by 2. And I'm like, oh, these two look exactly the same, all multiplied by 2. And I was thinking, okay, maybe they can be combined together. Yeah, I just got a little bit around here, right? I was thinking about reverse it. All right, that's it. That's it for today. See you guys tomorrow. Adios.